Hello, everyone, and today I would like to have, or I will tackle about my reflection about how CPU is made. So, about semiconductor manufacturing, a process that powers everything from our smartphones to our computers to the medical devices that save lives, and about this journey of conduct semiconductor chip from simple quartz sand to a complex microprocessor is both intricate and fascinating. Recently, I watched a video that offered a glimpse into the clean rooms of Global Foundries, one of the largest semiconductor manufacturers, and I was struck by the precision, care, and technology involved. And as we dive into the stages of this process, from design to manufacturing to quality control, I hope to provide an insight into the complexities and the significance of semiconductor manufacturing. First is design phase. Okay, let's start with the design phase. The blueprint of the semiconductor manufacturing is the design phase. The process begins at design centers spread around the world, where engineers collaborate to create circuit diagrams for integrated circuits or for short ICs. Okay, this design can be incredibly uh, sophisticated, especially for circuits that enables microprocessors and wireless communication in our devices. This phase requires expertise from many fields, including electrical engineering. Next is the computer science, and to ensure the final design is efficient, reliable, and compatible with other technology. Knowing this, I realized how this phase alone speaks to the global nature of the semiconductor industry. Engineers from different countries and cultures work together, often in real time, to design circuits that will eventually power our daily lives. This cooperation shows how the tech industry transcends borders, and with international teams driving innovation and setting standards for global technology. It's a reminder of the importance, okay, of collaboration when pushing forward complex advancements. And next comes the manufacturing silicon wafers, which are the base materials for microchip. It's fascinating to think that these wafers actually begin as quartz sand. Okay? This sand is refined to create pure silicon, which is then melted, and a monocrystal is drawn from the silicon melt. The silicon is sliced into wafers, which serve as the foundation for building microchips. Okay, so that's the base of the microchips, the silicon wafer. Inside the clean rooms, which are about 100, 100 times, 100,000 times, okay, yeah, 100,000 times cleaner than an operating room. Everything is done to prevent any contamination. Workers even wear specialized suits, and the air is filtered meticulously to keep the environment particle free. So even the workers is moving there so clean. They prevent using any suits that are not cleaned for the process to done clean cleanly. And reflecting on this level of precaution, wow, I realized that even the smallest particle could compromise a chip's function, underscoring just how delicate this process is. The clean room the clean rooms aren't just a technical requirement, they symbolize the high standards and precision that are essential in this industry. Okay? And one of the most remarkable steps in semiconductor manufacturing is photolithography. In this step, circuit structures are printed onto the silicon wafer using ultraviolet or UV light. This process involves coating the wafer with a photosensitive resist, then exposing it to UV light through a mask. The areas exposed to light are chemically altered, allowing for selective removal in later steps. After developing the resist, the unprotected sections are etched away and creating tiny transistor structures. This technique is fascinating not only because it's precise, but because it's the point where the design becomes a physically reality. Photolithography is like an uh, intricate art form where light and chemistry meet to create patterns that are invisible to the naked eye. Okay? I'm reminded of the importance of tools and technology in turning ideas into tangible products. Without advanced photolithographic equipment, the complex circuits in today's devices simply wouldn't be possible. And next is the ion implementation and doping, doping. After the photolithography, next critical step is ion ion implantation. In this process, the electrical properties of the transistors are determined by introducing dopant atoms into the silicon lattice. This step is crucial because it makes silicon a variable conductor. Its conductivity can be adjusted by adding the specific atoms which are fixed in place during a high temperature treatment. Knowing this, I find it more incredible how scientists can manipulate a materials like silicon at the atomic level to achieve desired electrical characteristics. And this process exemplifies the precision of semiconductor manufacturing, where even the atomic structure is engineered to create the functionality we need in our devices. It's humbling to think that the ability to adjust electrical properties so precisely is what makes computing possible. The next phase involves creating interconnection between billions of individual transistors on a wafer. Copper wires are used to form these connections, and a special barrier layer is applied before the copper is added, and to prevent short circuits. Each wire plays a role in linking transistor into a functional circuit. Okay? And this reminds me on the remarkable intricacy in chip manufacturing. Billions of transistors must work seamlessly together, and each connection has to be perfectly crafted. Knowing this, I can see the semiconductor manufacturing is a work of precision on an unimaginable scale. Next is, after circuit integration, next is the manufacturing process. moves to monitoring and quality control, crucial stage that ensures each chip meets high standards. Electron microscopes are used to monitor the process down to the atomic level, inspecting every transistor to ensure its function as expected. Okay? And my reflection about this is I'm struck by the level of skill, okay, from technology and dedication involved at each stage. From the initial design to quality control, every step in this process contributes to the creation of a chip that will drive future innovation. Watching a chip come together is like witnessing a combination of art, science, and engineering. And it humbly to think about how much effort goes into the devices we take for granted. And looking forward to the uh, advanced technology like now, and it's so marvelous. And that's all. Thank you.